Next speaker is Alex Merritt. Alex is the founder and president of Canary Systems. He has been working in mining industry nearly all his entire career, close to 40 years. This includes a decade at Geocon, manufacturer of geotechnical instrumentation, and then starting Canary Systems 28 years ago, founded to a specialist in instrumentation, monitoring system, and developing a comprehensive data management platform for geotechnical and geomechanical risk management. Alex is going to present on use of machine learning technologies to improve risk management in mining.
Thank you, Arzu. A few public service announcements before we get started. First of all, the presentation today is based on a paper. We decided to not publish the paper. At some point, I believe we will, but didn't seem the right time at this moment. Also want to thank Will Conrad. He's here in the audience. He's our Mine Solutions architect. He helped out with the materials for this presentation. Also, Alexei Suvorov, our lead software architect at Canary Systems. I also found out this morning 20 minutes includes Q&A, so I prepared 20 minutes of material, so I'll try to go through it really quickly. We'll probably skip a few slides, try to leave a few minutes at the end for Q&A. If we're short on that, you're welcome to come approach me after. I'd love to chat further with any of you about these exciting new technologies that we have. Sean actually provided me some introduction to some of what I'm going to share today, so he actually saved me a little time, so I appreciate that. We'll skip the table of contents. We'll get to it soon enough. All right, this is the audience participation portion, so any guesses what happened on November 30th, 2022? It was a hugely important date in the development of artificial intelligence and related technologies. Any takers? No? Okay, I'll give you a hint. I even got a graphic for you. No? Come on, I got this like stress-relieving squishy to give away to whoever gets it. All right, did somebody have it? ChatGPT. Exactly. This was really an important moment because, yes, artificial intelligence, as Sean has talked about, has been around for a while. We've been dreaming about machines that can think for a long time. There was a seminal paper written actually in 2017 by a bunch of Google engineers. They took the existing ideas around just forming knowledge in neural networks and added this idea of a transformer. It's not really, in my view, like the right word. It was the idea of attention. And a way that I understand this in artificial intelligence is actually the way our brains work. When we're thinking about certain information, like say we're trying to solve a math problem. Well, if you want to solve a math problem, you can't be thinking about the groceries that you need to buy on the way home from work. You have to pay attention to that domain. So there's a context in which you can be much more effective at solving a certain problem. And that's essentially what they were able to describe mathematically. That really led to an explosion of research and improvements in these technologies, culminating in ChatGPT being released in 2017 or 2022. Sean mentioned AlphaGo. Well, as a result of this paper that was written by the Google engineers, AlphaGo Zero was developed. AlphaGo Zero, using this transformer idea, not only learned the game of Go, but then beat the prior world champion, which was also the predecessor program called AlphaGo. So not only did it learn the game with really no instruction, but then it beat the reigning computer champion 100 games to 0. So this was really considered an important moment, this idea of transformer technology. So what's ChatGPT got to do with it? I'll give you the story. Everything. Really, so much has changed in just the last couple of years. You've seen that in the news, many different models being introduced. Recently, the Chinese even released a downloadable version called DeepSeek, which appears to work really well. Sean mentioned Anthropic. I'm actually going to do a demo with you using one of their tools called Claude and how it can be used to to help us solve problems. There's been just an explosion of technologies and ideas around these technologies in just the last couple of years. Now, how does this relate to risk management in mining? Well, imagine now all of these domains are like part of your brain. So general practices, soil mechanics, structural mechanics, general materials science, machine learning methods, statistical functions, rock mechanics, Python coding. You just got an IQ of like 400. And yes, I Googled that. That's apparently the highest score on record. You just got this amazing IQ because the tools actually take all of this information and allow you to solve your problems by posing questions to this amazing brain and get the answers back in various forms. And we'll do some exercises to show how that works. First exercise. When we observe failures in mining, we basically describe them in these three ways, because this is what we see. We see these progressive types of failures. Things are moving. You have a ramp that's just falling down because of gravity. You have yield or loss of strength. So a structure is being loaded, gets to a point where it can't handle that load anymore, and it gives way. And then last, you have spontaneous. So something just breaks. Oftentimes, it's due to operating conditions. You have a blast that introduces high energy into a structure, and it overcomes the strength of that structure, and it fails. Okay, so let's say we want to visualize these in a chart. Well, let's ask Claude. So Claude is one of the tools from Anthropic. And I'll show you in the demo here, what I did was I recorded me asking Claude how to visualize these three kinds of failures. So I'll start with just a question about rock mechanics, like to set a context. Remember this idea of the transformer idea. There needs to be a context to your questioning. So I start with a question, just a general question about rock mechanics. And I just ask it for what are the failure modes in rock mechanics. Claude comes up with a great inventory of answers, but this isn't really what I'm looking for, right? I'm looking for a visualization around these different failure modes. So, next question. Let's ask Claude to visualize these different failure modes. Let's see if I can get rid of there we go. You'll notice like in that center edit portion, that's where I'm typing in my questions to Claude. So I ask it to create a chart showing progressive failure, yield failure, and spontaneous failure. Claude thinks for a second and not only produces the answer, but also produces the code. In this case, it's producing React code because I didn't tell it which code to produce. The demo I'll show in a few minutes will produce Python code. It produces like mermaid chart. I didn't tell it what chart to make, so it just made the one it thought I wanted, which is not really the case. So let's go back and ask Claude for the chart I want, which is going to be a line chart. It produced, I believe these are called mermaid charts. So it shows the different failure modes and then color-coded to extent. So I ask it to modify it as a line chart. Goes back, updates the code. That code is what's actually producing the chart. So if I'm in a development environment, for example, this code is now exportable into that environment to reproduce this product. So it produces the chart. Now, in my experience working with this type of data, this is not really that accurate. For example, the progressive movement line, which is the blue, basically looks more like kind of a yield point curve, right? It gets to a certain level and then fails. So I'm asking Claude now to modify this to be more of a progressive movement as opposed to a progressive failure. So again, Claude interpreted my question pretty literally, and according to its understanding of failure, described it as failure. So it updates the code, reproduces. Now you see more of a predictable movement. Now let's look at the yield line. So again, in our experience, this is not a typical yield failure. Typically, yields mean you have a complete or close to complete loss of strength. In Claude's idea, you still have some nominal strength. This is the red line that you see in the chart. So I asked Claude. Now, interestingly, notice I misspelled my question to Claude, and yet Claude still knew exactly what I was talking about. It just ignored my misspelling. So again, you can see the effect of context in all of the questions. It's building on my queries one by one to produce the kind of output that I'm looking for. This is what's amazing about these tools. If you know the questions to ask, it will produce the kinds of outputs that are really helpful and meaningful for you. And in this case, producing software code that can be used or transported to other systems to then present these visualizations or these findings in other platforms. Okay, so before we get to our second exercise, let's talk about some of the basic challenges with implementation of machine learning. It's been talked about a little bit, some of the challenges with data. I summarize them in these 7 ways. First, spatial awareness or proximal awareness, like where is data in relation to each other? What about time normalization? So many types of data come in with different timestamps. Some data may be daily, some may be weekly, some may be monthly. To be able to analyze this data, you've got to normalize it to the same units. Units normalization. If you look at a big open pit mine, you have piezometers measuring pressure, rainfall measuring millimeters or inches of rain, prisms measuring movement. How do we normalize these units so that you can actually compare them? We'll use, in our example, acceleration, which is kind of a universal unit. Then what are the relationships of this data to each other? Like how do these measurements actually correlate or influence each other? Then how do you select the prediction methodology? There's thousands of ways of predicting data. So which one do you use? What is the confidence that you can have in that prediction? And then last, support from stakeholders. So one of the challenges we find in implementing these systems is just getting buy-in from operators of mines. You can see here at SME, 90% of the exhibits are around production, around producing the minerals or the extracts. But yet risk management is hugely critical to the operation of a mine. If you don't manage risk effectively, you run the risk of people dying, health and safety concerns, production reliability. So hopefully over time, we are seeing this, that there is more support from stakeholders for these types of systems and this type of data analysis. Okay, so this is the workflow that we followed for our exercise number 2. So a basic kind of use of these tools to produce a machine-learned methodology or programming set to be able to process data in a more powerful way. So first of all, you have your input. So as you saw with Claude, you can actually upload files. You can explain to Claude what those files are. So if it's a prism, what is the data? Claude actually understands GIS systems, but it doesn't always understand the data. So you need to explain it to Claude as if you're talking to a person. Then you attach your sample data files, then you describe your output. So if you want all of your data, for example, normalized to a certain time or a certain unit type, you just ask Claude to do that, and the tool will produce the code that actually will perform that for you. The middle part is kind of the meat of this whole process. And understand it's an iterative process. So first asking these tools for their interpretation or understanding of the data. What do they see in the data that you may not be seeing? You ask for the code that's produced as a result of that exercise. And then based on the results of that code running, you validate that against the observations that you've made. So for example, if you know that there's been movement in a pit, and a certain prism or a certain monitoring asset indicated a partial failure, that becomes a way to then validate the results of this code that gets generated. And then last, once you're confident that you've come up with a system to identify these types of risks, that code now needs to be generally repackaged for the platform that you're running. So we're still within our tool, right? We're still within Claude. So how do we get from Claude or ChatGPT to whatever platform we're using? So that's the output process, taking that code, forming it to work within the environment that you're using, converting the output data forms, and then ultimately posting that data in some way into your system. I'll demonstrate that in this second exercise. So we use Claude to produce a Poisson probability of prism data. So in our case, we found a 2-week rolling window, worked really well to be able to predict on a 24-hour basis the probability of 0.2 feet per day being achieved. Now again, there's a bunch of assumptions in there about the thresholds, and that process of what I've just explained took a lot of questions to Claude. I just gave you the 20-second version of what took several hours. But in the end, this tool produced code that allows us to now analyze this data in a much more meaningful way than we had been doing before. A couple screenshots on how this works in our platform. So this is an example of where this script gets loaded. We show the Python form of the programming. We then schedule this for every minute. So in the demo, which I'll start here, so we're processing a group of prisms. They're actually shown in this map view on the left. It's calculating accelerations over 30 days. And then it's calculating this 14-day window, and what is the probability of this 0.2 feet per day being exceeded. So I sped this up. This was running for a month, or I should say it was running on a month's worth of data every minute. So it took 30 minutes to run this. We sped it up into like a 2-minute video. So you'll notice there was a point where movement in a group of prisms was observed. The probabilities, you can see on the scale in the lower left, it goes from 0 to 1. We set thresholds for alarms. I was not fast enough in highlighting how those alarms were visualized. There were some like little halos that showed up around some of the prisms to show that alarm. But ultimately, these tools allowed us to develop this sophisticated programming in a fraction of the time that it would have taken to develop it using an actual programmer and working through these data types that are really quite, have a lot of discontinuities in them. The tool allowed us to very quickly form a normalized data set in time, in units, and in space, and be able to produce code that gave us much more sophisticated analytics around how to use this data. And now the data can inform around risk that this mine has experienced in the course of their operations. All right, we'll go to the next slide here for sake of time. How are we on time? Oh yeah, I gotta talk faster. Okay, we'll wrap up with a few summary slides. Keys to success: know your domain. One of the challenges with these tools, if you don't know what you're doing, you're not going to get good results. Second, more data, better results. One of the initiatives we're really pushing with our clients, for example, is getting production data. See how the production of the mine relates to the stability of the mine. The question is the answer. These tools force you to really think about the problem you're trying to solve and what questions you need to ask to be able to get the results that are really helpful to you. Have a platform that you can use to access the data and run these different scripts, and be curious. Your brain just got really huge with these tools. So use your brain and these tools to do much more meaningful analytics and understandings of data. There's a lot of future research. I see this time that we're in right now as really exciting, and we're really just beginning this process of using data much more meaningfully with these tools. We want to integrate other types of data, including geological models. We want to understand the relationships between data, improving thresholds, metrics for risk management criteria. A lot of what we're able to understand is just based on our viewing of data, but we want more sophisticated ways of doing that, perhaps using these tools for that. Incorporate more failure training data. If any of you have failure data, please get my card and email it to me. We would love to get copies of that. And then in the future, we see incorporation of these AI engines directly in platforms. We see that coming really very quickly. All right, last, should we be worried? Absolutely. We live in an amazing time, and these tools are amazing, but there are a lot of concerns and fears about these tools. Now, I will say the media completely has it wrong. The media would have you believe that AI is going to take over the world and humans are going to be irrelevant. That is far from the truth. I believe the reality is the problem is humans using these tools in ways that they don't understand and getting outputs that are harmful. I'll take an example of self-driving cars. I don't see us anytime soon, if we're in a self-driving car, that car pulling up alongside the curb and asking you to get out so it can go for a joyride. That's kind of how the media presents it. It's really more an issue where the AI in these cars will make a wrong decision, or we will give it a wrong direction and it will drive off a cliff. That's the danger of these tools. So in the context of risk management, it means if these tools are not used well, it means risk will be either underreported or overreported, and neither of those scenarios are good for our business. Thank you.